Hi everyone, this is Team Artemis, and our project is about signature verification. So basically, signature verification is to check for authenticity and to validate the identity of an individual. It has wide application in banks, intelligence agencies, and other institutions. Verifying the identity of a person using handwritten signatures is challenging in the presence of skilled forgeries, where a forger has access to a person's signature and then deliberately attempt to imitate it. In offline signature verification, the dynamic information of the signature writing process is lost, and it is difficult to design good feature extractors that can distinguish genuine signatures and skilled forgeries. So our task here is given a picture of signature and then identify whose author it is and if this is a true signature or a skilled forgery. Our data set is from ICDAR 2011 Signature Verification Competition. We use its offline signatures in both Dutch and Chinese. We have in total over 2,500 genuine signatures and skilled forgeries. So here are some example signatures. We noticed that the skilled forgeries actually resemble the genuine signatures to a large extent.
Next, I'm going to talk about our approach. Our original thought was to use Siamese network to project the signature images onto the feature space and calculate the distance between a pair with cosine similarity. However, we found that this approach has rather poor performance, so we turned to a two-step procedure described in Haveman's paper using CNN feature extractor and writer-dependent SVM. After a series of pre-processing, such as removing background, normalizing, we plug the cropped signature image into the CNN, consisting of 6 convolutional layers, 3 max pooling layers, and a fully connected linear layer that outputs features with dimension of 2048. The features are fed to the next layer that fulfills our 2 tasks. We employ multitask learning in our CNN model, namely, both to classify the user and identify whether it's a forgery. Therefore, our loss function is the weighted sum of the 2 cross-entropy loss. Note that we subtracted the multi-class cross-entropy loss of forgeries because we don't really care which user the forged signature belongs to if we identified it to be a forgery.
After training CNN to extract features, we use writer-dependent SVM for final verification. The graph shows how we emulated application scenario. Users are split into dev users and new users. We train one SVM for each user using some of his or her genuine signatures as positive and forgeries for other users as negative. Even the forgeries for this user are only used in validation. This approach works surprisingly well. Next page shows the model results. We use TSNE algorithm to visualize the features in a 2-dimensional space. As shown in the figures, the CNN successfully transformed the features to separate genuine and forgeries. Next page shows similar transformations for Chinese signatures. For the validation dataset, we can see the genuine signatures are not all grouped together. Therefore, we train SVM for each user to tackle this classification problem. Next page is the evaluation of our signature verification system. We calculated the FRR, false rejection rate, FAR, false acceptance rate, and EER, equal error rate, which is the error when FAR is equal to FRR. For both Chinese and Dutch signatures, the best performances are achieved by using SVM with RBF kernel and user-specific thresholds. That means user-dependent classifiers are effective. The Dutch signature classifiers achieved the EER around 3.5 and AUC more than 98%, which are close to the state of art. The performance of Chinese classifiers is inferior, which might be due to the more complex signature structures. We'll continue to work on that. Well, thanks for watching, and please ask questions to help us improve.